Hello again, and thank you for joining us on another episode of Space Nuts. This is a Q&A edition where we take audience questions, we put them on paper, and then we put them on a roll that goes on a little thing in a bathroom. Or we could answer them. We can do that. Coming up today, we have questions from John about Martian days, the length of a Martian day. It's close, but is it close enough to Earth standard? We'll discuss that. The growth of a black hole has been brought up again. We've got a question from an 11-year-old named Thomas. Hi, Thomas. He wants to talk about the Galactic Center, and Paul is asking about our galactic location. So we'll deal with all of that today on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us again to sort all of that out is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see you again.
Good to see you too.
Yes, despite the hole in my head.
Yeah. It doesn't look any better than the last time I saw you.
It doesn't, does it?
No. I mean, it's only been minutes. You'd think it would have improved by now.
You would. That's what happens when you walk into a closed screen door.
Yeah.
In the dark.
It hurts.
It hurts, yeah.
Now, that's why they have stuff on glass sliding doors, That's a standard, safety standard required these days so that you know the door is there.
Yeah.
But when it's nighttime and it's a screen door, not many excuses left there, Fred, really.
Only stupidity, I think, is the last one, but that's my excuse many, many times.
Yeah. Well, like I said before, we've all done it. Shall we try and answer these questions?
We should.
Okay. Let's go to question 1. This one comes from John. We know that the Martian day is 39 minutes longer than an Earth day. That's about 4.5 hours a week. When and if Mars is populated with humans, how would we work with the longer day/week? Would human biology tend to keep to the 24-hour day, or would we adapt to a longer day-night cycle? Thanks, love the show, and have been a listener since you started. Wow, you've got a lot of spare time, John. Thank you so much for sending your question in, and hope all is well. I love this question because you've got a planet that is close enough for us to get to in the not-too-distant future, probably not a permanent settlement, but a rotating settlement of some kind will be the initial stages of humans being on Mars. And yet, you've got an extra 39 minutes a day to deal with. What is going to be the impact?
I think we've already
got
a lot of data on this because
we've already talked about this once before in the deep dark past, but
quite
I'm glad
a long
it came
time
up
ago.
again.
Yeah, because of the rover drivers. The people who are in command of, if I can put it that way, because they don't actually drive them directly, but in command of the rovers on Mars, and the two active NASA ones at the moment are Curiosity and Perseverance. They adapt to a 24 hours, 39 minutes day, and do it quite successfully as far as I've been able to work out.
Well, I hope so.
Yeah, otherwise there might be a pile-up on Mars. And in fact, the reason why I said they don't actually drive them is because the rovers themselves have got to be, to some extent, autonomous because of the delay in signal time to get between Mars and the Earth. You can't have video coming back from your rover and a steering wheel so that you respond to that, because you'd have a sort of 20 or 30 minute delay probably before the wheels turned on the rover.
I would imagine that the manual driving of a rover from Earth on Mars would be damn near impossible, because even your images would be out of sync with reality.
Everything's out of sync, that's right.
So you say, there's a rock coming up. That was 40 minutes ago. I'll turn left. now.
Yes.
Oops. Yeah.
So the rovers drive themselves basically, with a lot of assistance and monitoring from Earth, in order to see what's coming up and see what the onboard computers are doing in terms of what route they're taking through the rocks and debris on Mars. But those people, as I understand it, do go on to this 24 hours and 39 minutes day length. I think it's near enough to our 24 hours that I think they adapt quite quickly from my recollection of our previous conversation about this, Andrew.
Mm. Yeah, if I remember rightly, we were talking about the fact that if you're going to stay on Mars long term, you would have to adapt. You wouldn't adapt naturally at all. You'd have to take cat naps or something like that to catch up, or something to that effect.
Well, yes. So your circadian rhythms they'd be under stress. They'd change. And I suppose you'd have a permanent feeling of jet lag, probably. That's probably what it feels like.
It would be tough. I read an article last weekend, which I found fascinating, and it was detailing how the 8-hour night cycle that humans have, like going to bed for 8 hours, is a myth.
Yes.
And that it was actually something invented by a mattress company back in 1938. Have you heard this?
No.
Yes.
I do know that we used to sleep twice in the night.
That's right. So you go to bed at like 9 o'clock, and you'd sleep for 4 hours, and then you'd get up for 2 hours and you'd do stuff.
Yes.
Like stuff we can't talk about on this podcast, but other stuff like they cited a couple of famous people whose names have dropped straight out of my head. William Shakespeare apparently wrote a lot of his famous works between 1 and 3 in the morning when he got up, and then he'd go back to bed for 4 hours. And Beethoven did the same thing with some of his symphonies. He wrote some of the best works that he ever created at 3 o'clock in the morning. During his wake time between his two sleeps. Yeah. So the 8-hour sleep that we have at night was an invention, apparently, to sell mattresses. That's what I'm told. Look, I haven't confirmed or denied that, but it seems possible, I suppose.
Well, yes. I mean, I think there's been evidence from the earliest times. The times when people truly were ancient peoples back thousands of years ago, that's how they lived their lives, exactly as you've said. And maybe there were the last vestiges of that were keeping going in Shakespeare's time and then in Beethoven's time. There weren't that many clocks around then. There were some, but not that many. It wasn't like you had a smart watch by your bedside or anything like that. So it would be a natural rhythm that they would use to sleep and wake up.
Yes.
And if you're natural,
modernisation certainly messed us up, hasn't it?
Yeah, that's right. I think in that case it has.
And I think on Mars it will be a pretty difficult thing. I imagine
it may be. So maybe I can just sidestep here slightly, Andrew, because I would very much like to know what answer one of our listeners would give to that, and that's Dr. Heidi de Block, who's I think based in Houston, if I remember rightly, who is basically a space medic, and it will be very interesting to hear her take on how humans will adapt to that. And if I may, she was in touch with us recently to comment on one of our earlier questions. Would it be all right if I read that?
And that was when we were talking about how people deal with gravity when they get back on Earth after being out in space for a while.
Correct. Yes, that's right. She says, I just finished the July 5th Space Nuts and wanted to help answer the question about how the astronauts feel when they land back on Earth. Of course, I haven't experienced it in person, but have worked with plenty of astronauts at landing in particular. all of our physiology changes in space as we are designed for 1G. Some astronauts are pretty good when they land, especially those who were on the shuttle and in space for a short time. Some had significant problems. They stem from the orthostatic hypotension as a result from the cardiovascular changes. Some of the changes in the inner ear with balance and knowing where you physically are, some mild weaknesses, etc. These changes are more exaggerated with long-duration flight in the International Space Station. The vision problems are called SANS, S-A-N-S, which is an acronym for Spaceflight-Associated Neuroocular Syndrome. Our lab is studying that as well. That's a whole other fascinating issue. I could tell you some fun stories about astronauts and how weird some of them feel when they get back. Maybe we need to get Heidi on the show.
Maybe we do.
Yeah. No, that's she has another interesting comment actually about the Voyager Golden Record, but we might talk about that another time.
Fair enough. Yeah.
Yes.
All right. Thank you, Heidi. That was fascinating. Yeah. What an amazing job working with all those incredible people.
Yeah,
trying to figure out how to deal with the 0G problem. But on Mars, the gravity will also be an issue. So there's a heck of a lot that needs to be sorted out before we put people down there, because it's such a long trip to get there. It's not like you can go, oh, no, this is no good, and come straight back. It's not going to be that simple.
No, that's right. Once you're on your way, you're on your way. And the only way back is to keep going.
Yeah, exactly. Yeah. Thanks for the question, John. Well asked. And it's not going to be a snack, that's for sure. Let's move on to our next question from Dan.
Hello, gentlemen. Dan from the Gold Coast here. Now, I know you've been asked a million questions about black holes, but I do have a quick two-parter, and I'm hoping it's something you've never had to answer before. Really quickly, from the point when a black hole is born, birthed, created, whatever you want to call it, how quickly is that growing to become a, let's say, supermassive black hole, or just something a lot bigger? Or is that not how black holes work and I'm not understanding it properly? 2, hypothetically, if there's no matter or energy or anything surrounding the black hole to take in and, let's say, eat, is the black hole still going to grow? Is there more to the black hole growing than I understand? Hopefully that made sense, and hopefully it's worth answering. Love the show. Love you guys' work. Cheers. Bye.
Thank you, Dan. Nice to hear from you. A couple of questions in that one. We never talk about black holes, but we will today. Speed of growth. That's an interesting one. Given that we're starting to think that there were some absolutely enormous black holes in the early universe, and that they're looking for more and more evidence to see what was going on early on. But we've got some gargantuan ones still around. So how fast did they get that big? And I'm starting to think, Fred, it wouldn't be a stock standard approach.
Maybe not. But Dan's asking one of the fundamental questions of astrophysics at the moment. This is a very hot topic. And what set the cat among the pigeons and made it a hot topic is the James Webb Space Telescope. Because until that came along, the idea was that, as Dan suggests, black holes were formed in the early universe by exploding stars that collapsed at the end of their lives to form a black hole. The core would collapse to a black hole, and that then over billions of years, that black hole would grow, and eventually, in our own epoch today, 13.8 billion years after the Big Bang, you have supermassive black holes at the center of every galaxy. That was the old wisdom, but the James Webb Telescope has turned that completely on its head, because we have serious evidence of supermassive black holes within the first 500 million years of the universe's existence. And that's too quick or too short a time for this, this slow accretion of stuff as being the the growth mechanism for black holes, it's too short a time for that to be the case. So either our ideas of how fast they gobble up matter is wrong, and they gobble up matter a lot faster than we thought. And we actually covered a story on this, I think, about 4 or 5 episodes ago, because there are some scientists who came to the conclusion that one of the things that we thought limited how fast a black hole can gobble stuff up was actually invalid under certain circumstances. So that's that one avenue of research that's come from the James Webb Telescope, showing us that we've got these supermassive black holes in the early universe. But the other one is the idea of the little pink dots, or the little red dots as they're called. Yeah. And these are thought to be basically just clouds of gas, hydrogen gas, which are directly feeding a black hole that may have been formed in the Big Bang. In other words, you didn't have to have star formation and then stars blowing up to create black holes in order to kick this process off. The Big Bang itself might have kicked off the process of black hole formation by producing these things that we call primordial black holes, and they may have turned out to be able to grow very quickly by immersing themselves simply in big clouds of hydrogen and gobbling it all up.
Yeah. Of course, when they run out of stuff, they can't grow. Is that right?
That's right. So that's part 2 of Dan's question. What happens when there's nothing there for them to eat? And they become what we call quiescent black holes. They don't do anything. They're there, and they're still things that if a cloud of hydrogen strayed by, they might seize it by their own gravity and pull it in. Yeah. But they're not going to go out roaming through the universe looking for stuff to accrete. In other words, looking for a snack.
Yeah, I used to work with a guy whose nickname was Quiescent Black Hole. He was there, but he didn't do anything.
Yes, I think I know who you mean.
Oh, dear.
Yeah. Anyway, quiescent black holes are basically what Dan has described. But the first part of his question is absolutely asking the same questions that today's astrophysicists are. It's one whose answer we don't know, but the consensus will emerge over the next probably not very long, because we're getting so much data from the James Webb Telescope that I think it'll be quite soon before this whole issue is resolved.
I would think. Sorry.
I was just going to say, when there is hard evidence of a primordial black hole being discovered, one that was created in the Big Bang, then that'll be Nobel Prize-winning science when we get to that stage. Yes. But it won't be us.
Indeed. I was going to suggest that black holes are probably like humans. Consumption will decide how big they get.
Maybe, that's right. Maybe. Yeah.
We'll have to wait and see. All right, Dan, hopefully we covered that for you adequately. Thanks for sending in the question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Our next question, Fred, comes from Thomas Reid. Thomas is 11 years old. He says, something has been troubling me in books I've read. They say that the centres of galaxies are very big black holes. And I have a few questions about them, but I'm only an 11-year-old kid. So the questions might sound silly, but here they are. Now, we've got 5 questions, Fred, so we can be brief on them unless you want to sit here for another couple of hours. If Jonty was here, we would be a couple of hours. Can the galactic centre swallow all the stars and planets in the galaxy? How big are the galactic centres, or do we not know? If they can swallow up all the stars and planets, is there a limit? If there is a limit, what is it? And if there is a limit, what happens when the limit is reached? Thank you for taking the time to read this, and I would love it if you could reply. Well, we are going to reply right now, Thomas. Yeah, it's great that somebody so young is taking a keen interest in something so mysterious as a black hole. We'll want to start at the top. Can the galactic centre swallow all the stars and planets in the galaxy?
Well, so the answer is no. So the galaxies are very big. Ours is about 100,000 light years across. Black holes have a kind of sphere of influence which gravitationally stretches to the edge of the galaxy. But by the time you get there, the gravity of the black hole is very, very weak indeed. And so it's only in the central region of a galaxy where you could get material being swallowed up to create this activity that we talk about when we talk about active black holes, where there's an accretion disk, a disk of material swirling around it, and these jets that point basically at right angles to the accretion disk, jets of material traveling at nearly the speed of light. Quite extraordinary. So that's all great, and a black hole's like a factory or a furnace doing that, but its stretch is not very far. It's measured in light years, but not in hundreds of thousands of light years, which you'd have to be to grab everything in the galaxy. So the answer is no. The galactic center black hole cannot swallow all the stars and planets in the galaxy.
So Thomas can sleep well tonight. How big are the galactic centers? Do we know how big the middle
we
is?
do. Yes, we do, because we can measure the speed of rotation of stuff swirling around a black hole, if it's an active one.
Yep.
And that directly tells you the mass of the black hole. Because the bigger the black hole, the faster the stuff is going. And so in terms of, if by big Thomas means what's their mass, we can measure them quite accurately. Now, because we can measure their mass, we can also work out their event horizon diameter or radius. The event horizon is that sort of imaginary sphere around a black hole beyond which light cannot escape, and so it would appear as a dark sphere. So the event horizon is the point of no return for anything going into a black hole, and it's also the point of no escape for light waves. So we can, knowing the mass of a black hole, we can calculate how big that event horizon would be. And some of the supermassive ones are really very big. They're measured in light years, tens of light years perhaps, for the supermassive black holes.
Yeah, it's a level of enormity that you just struggle to get your head around.
Yeah.
I suppose in terms of the rest of Thomas's questions, you've basically answered it with the answer to the first question, because he's asking if they can swallow up all the stars and planets, is there a limit? If there is a limit, what is it? And if there is a limit, what happens when the limit is reached? Well, the limit is probably the local area of the center of the galaxy and what's available to eat.
Yes, that's right. So the limiting factor is basically what you might call the grasp of the black hole, how far it can reach to pull something in. And that is dependent on how fast the objects are moving. So you can have some stars, and there are some, we've observed them with infrared radiation, that are comfortably in orbit around the black hole at the center of our own galaxy, which are not being pulled in, they're orbiting, and that's because their speed is enough to keep them out of the grasp of the black hole. Their distances from the black hole are measured, in not too dissimilar units from the solar system, sort of half a light day or something like that. Light day. That's the sort of measures that we're talking about, which probably denies what I just said a few minutes ago about some black hole event horizons being tens of light years. I don't think they are. I think they're smaller than that.
Okay. I've thought of a way to explain it to Thomas. So, Thomas, you've won a competition and you can go to McDonald's and eat everything you want. Absolutely. Just keep eating until, the cows come home. However, you aren't allowed to move from wherever you're standing, and you can only eat what's within reach. Once you run out of food, you stop growing. And you're the black hole, by the way. How's that for an analogy?
Yeah, it's a nice one. I like it. Yes. Yeah, because your reach is the sort of gravitational force that you can exert. Yeah, it's a good way of putting it, Andrew. Well done. You should be on the radio.
I try to think on an 11-year-old level, but I'm thinking Thomas was probably much brighter at 11 than I was.
Struggle to get to 11, so do I.
Yes. Thanks, Thomas. That was really terrific. Thanks for sending it in, and keep on listening.
Houston, Tranquility Base here. The Eagle has landed.
Space Nuts.
Final question, Fred, comes from Paul.
Hello, Space Nuts. Paul here from sunny Brisbane, Vegas, where it's currently bucketing down in what is being described as a rare rain occurrence. Anyway, I am currently looking through a very old book of mine. I guess it's old compared to the students I teach. It was published back in 1978. I think I got it in 1980 from an uncle of mine, Uncle Jim. Thank you very much. It's called Stars and Planets, and it's probably what got me into the whole field of astronomy in the first place. At least my interest in astronomy, obviously. Very, very grateful. I'm on the page where it's talking about how the American astronomer Harlow Shapley used the 1.5 meter reflector on top of Mount Wilson in California to work out that our sun is not at the center of our galaxy, as was previously thought, but is about 2/3 of the way to the edge. Could you please give us some idea how he actually managed to do that? Was it something about the density of stars? I mean, how many stars in the field of view when you point it one way compared to the other? How did he do it? I'm really curious, and I know I could Google it, but I'd rather hear it from you guys. So, thanks in advance. Love the show, and dare I say, keep up the good work. Cheers.
Cheers, Paul. Thanks for sending that in, sending the question in, and we don't know the answer, so but we're going to Google it. No, 1978 Stars and Planets. I tried to look it up. There are umpteen books named Stars and Planets.
Yeah.
So I haven't been able to, distinguish one from the other as yet. So, you'll have to do some fishing to find the book that Paul was talking about. But he wanted to know about the man who decided or discovered that the sun was not the center of everything, which was a common belief back in the day.
It was. It was actually 1919 when that discovery was made.
Was it that recent?
Yeah.
Wow.
It's one of my favourite astronomical discoveries, which is why I didn't need to go to Google to look it up. So it goes back to the time of William Herschel, who was a German turned British astronomer, worked late in the 18th century and early in the 19th century. He discovered the planet Uranus in 1781. But what he was doing when he discovered Uranus was actually mapping the Milky Way. He was observing the Milky Way in a very systematic way with a relatively small telescope. So he's sort of counting stars in the field of view of his telescope and then moving the telescope a bit further along the Milky Way, counting stars again, how many he could see in the field of view. And doing that and doing it, he couldn't do it all the way around the Milky Way because there's parts of it that he could never see because they're in the southern hemisphere, but he got round most of it. And what he discovered was that the star counts are pretty even all the way around.
Mm.
And so that led him to build the hypothesis that the stars are in a sort of flattened disk, which is correct, but that we're very near the middle, which is not correct. And the reason why he got that erroneous answer was that when you look through I think it was a 7-inch telescope, if I remember rightly, a telescope of that size at the Milky Way, the stars that you see are all relatively nearby. They're perhaps 1,000 light years away or something like that, maybe a bit more, maybe a couple of thousand light years away in the plane of the Milky Way. And that's partly because the Milky Way is very dusty. There's a lot of dust everywhere. It's probably better described as smoke, but we call it dust in the world of astronomy. And so that dust limits how far you can see. And so when you look at the Milky Way, it does look generally relatively even. There's one bit in the constellation of Sagittarius where it's brighter, and that's because you are looking towards, as we now know, the galactic center. But Herschel, he couldn't see that very well from the northern hemisphere anyway, but he did sort of discount that. He said, by and large, it's the same count all the way around, so we must be in the middle. roll on the years, and in 1919, Harlow Shapley, a very gifted American astronomer, although he did get one big thing wrong, but what he did was he was interested in objects that we call globular clusters. And so these are, in fact, they were named by William Herschel. He gave them that name, clusters of stars that appear like a globe. And Harlow Shapley was he was interested in globular clusters. He noticed there were a lot of them in our skies. They tended to be different sizes, and he didn't know whether that was because they were all the same size and some were nearer than others, or whether they were intrinsically different sizes. But what he did notice was that there's a concentration of them in the southern hemisphere sky. He was observing from California, so he could see a fair swath of the southern hemisphere sky. But he noticed that they were concentrated in that direction. And that made him wonder if that was where the centre of the galaxy lay, rather than us being near the centre. But then his other step was that he recognised that within these globular clusters was something called they called them cluster variables, stars that varied in a certain way with a periodicity of about a day. Today we call them Auroral Lyrae variables, and I actually started my astronomical research back in the 70s studying these things, Auroral Lyrae variables, and they are good because they've got basically a known distance. If you can see an Auroral Lyrae variable and identify it as one, you know how intrinsically bright it is, and then from that you can work out how far away it is. And so he found these variable stars in the globular clusters and recognized that he could draw a chart with the globular clusters all at their correct distance on it, make a kind of three-dimensional map of the sky. And sure enough, they concentrated around the galactic center, around a point. He actually got the answer wrong because his magnitude, his brightness that he had for the cluster variables was incorrect. And I can't remember what answer he got, but in modern parlance, it's about 25,000 light years. The globular clusters themselves cluster around a point about 25,000 light years away, which is deeply hidden by the dust clouds in Sagittarius. So he figured out that that's where the center of the galaxy was. A brilliant piece of detective work. We know he was right. What he was wrong about was he had a big discussion, I think in 1923, just before Hubble recognized that galaxies were big things a long way away. Shapley was arguing that galaxies lie within our own Milky Way, that they're small objects in our own Milky Way. Okay. And he was arguing, it was a public debate actually between Shapley and a guy called Heber Curtis. Curtis had the answer right. He said they're big and a long way off. Shapley said, no, they're small and nearby. And it was very soon after that Hubble produced that they're big and a long way, proved that they're big and a long way off. Yeah. So Shapley was wrong in that, but he was right about the galactic center.
Fantastic. Gee whiz. Great question, Paul. And if people are looking for that book, Stars and Planets, it is out there. Look, I've found a couple that were actually published around that time that Paul mentioned, but not sure if they're the ones. I can't remember the author now. That he said, but
I don't think he mentioned an author, did he?
I thought he did, but no, he might have mentioned an uncle.
It was his uncle he mentioned.
Uncle,
yes.
okay.
Uncle Jim.
He didn't write it. But so yeah, thanks, Paul. Thanks for the question, and it's a fascinating history in astronomy as we discover these things. I think one of my favourite moments, I suppose, in astronomical history was when they discovered that our sun was a star.
Yeah, that was a long time ago.
Yeah.
Yeah.
But for a while there, we didn't think of it like
thought
that.
It was something else. That's right.
Yeah.
Something a bit special.
Yeah. And I saw that on a BBC documentary many years ago, and I sat there and went, wow, I never thought about that, because I've always known it to be a star, but for generations they didn't. Quite intriguing. And why would you? It doesn't look like a star.
That's That's right. It's clearly quite different from a star.
Incredible. Thanks, Paul. Thanks for sending that in. And if you have a question for it, and thanks to all our sender-innerers. I've always wanted to say that, for their questions. And if you would like to send a question, go to our website, spacenutspodcast.com or spacenuts.io, and there's a little AMA tab at the top, which stands for Ask Me Anything. Not me personally, it's the royal me. And just put your question in there. It can be text or audio. Don't forget to tell us who you are and where you're from, and have a look around while you're there. Don't forget to leave a review at your favourite podcasting platform. We're all done. Thanks, Fred.
A great pleasure, Andrew. We continue to get great questions from great listeners, and long may it continue. Thank you.
Yes, indeed. We continue to solve and evolve. Maybe not.
I'm not evolving.
Once you reach a certain age, evolving just is not part of the program.
That's right.
Yeah. Ask my mum and the internet. Thanks, Fred. We'll see you soon.
Sounds great. Thanks, Andrew.
Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who's just turned up. We started 39 minutes ago, and Hugh set his clock to a Martian day, so that's why he's 39 minutes late. Boom, boom. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.